Hello everybody, my name is Kelby Eskibin. I'm here with my partner Alex Andreessen. Today we're going to be talking about our project titled Using an Energy Storage System to Estimate the Inertia Constant Within a Power Grid. Our project was advised by Dr. Ronaldo Tonkowski and sponsored by Ujwal Tamarkar of Sandia National Laboratories. Photovoltaics are revolutionizing the power grid with the benefits that it has, but with that means the displacement of traditional generators. For a stable and reliable power system, balance throughout is crucial. This balance is proxied with a stable frequency, and the displacement of traditional generation methods is leading to frequency stability issues. Severe system incidents may lead to large frequency deviations and cause cascaded tripping across a large area. Load changes throughout the power grid cause this change in frequency.
One of the biggest indicators of how a power system will respond to these changes in frequency is the overall system inertia. Inertia is defined as the amount of rotational energy provided to the grid at any given time, and is currently being provided by rotational-based generation methods such as coal-fired and natural gas plants. It is considered the first line of defense, occurring within the first 10 seconds of a frequency event. If the inertia constant is known, new control strategies can be implemented.
Our project aims to estimate the inertia constant within plus or minus 10% using an energy storage system. The figure below shows our technical solution for the project. On the left side, we have the energy storage system. This includes an inverter/charger that acts as a current source directed toward the battery. The OPRT is the brain of the project and controls the system as well as estimates the inertia constant. On the right, we have the power grid represented by a generator and a base AC load. To establish our power system, we use a 10.4 kilowatt generator, as you can see, connected up to a base AC load, as shown below here.
Our moving horizon estimation algorithm needs a large enough change in load and frequency in order to estimate the inertia constant. This was done using this Xantrax inverter charger pictured here, as well as this battery bank to the left. This Xantrax inverter charger was controlled via our RT Lab software in order to set the charging rate as well as turn the charging functionality on and off. The software control of the charger can be shown here.
Here is the OPRT hardware interface. As you can see, we have the voltage and current inputs.
Shown here is both the CAN communication with the Xantrax inverter charger, as well as the data inputs and outputs. The voltage and current measurements are taken in and are processed through a PLL to estimate both frequency and power. This data is then saved to a file for further use by the moving horizon estimation algorithm.
Here is a data processing block diagram of the MHE Simulink model. It takes the data saved from the OPRT and it runs it through the state equation, the governor, as well as the moving horizon estimation algorithm. The state equation is used for the validation of the inertia constant. The MHE block takes the power and frequency as inputs and outputs the estimated values of inertia, power, and frequency to MATLAB. Here's an example of the algorithm running.
The results for our first test case are shown here. We're using the energy storage system to disrupt the frequency. We have a change of load of 1 kilowatt and a pulse every 1.5 seconds. The algorithm was able to estimate the inertia constant within 9.5% accuracy. Here are the results for test case 2. We were using a manual load switch to give a change of load of 4 kilowatts. We had a similar 1.5 second pulse, and this was able to estimate the inertia constant within 4.8% accuracy. The inertia constant of the power system was able to be estimated within 9.5% accuracy using the energy storage system to increase loading, compared with 4.8% by switching the load manually. This project was the first aimed at using an energy storage system and a commercial off-the-shelf inverter to disrupt the frequency of a power system in real time. The main challenge we faced was attempting real-time estimation using third-party optimization software. We were able to effectively communicate with OPRT support in order to arrive at a potential solution to the compatibility issues we faced. However, with little time left in the semester, offline-based methods were implemented.
From this project, we learned and applied a variety of engineering skills, a few of those being communications using CAN to control the system. We also applied our understanding of power dynamics and learned how to control a power system. We also applied our knowledge of validating data with different measurement tools. As for the future of this project, the next step is to use the OPRT in unison with the MHE algorithm And even further, use this inertia in different control strategies such as virtual inertia and model predictive control, or MPC. Thank you.